Now, here the chapter 11, hyperfine structure, hyperfine structure, and the addition of angular momentum. And the quantum mechanics quantum mechanics was originated from the investigation of the hydrogen atom spectroscopy. When you see the hydrogen atom spectroscopy, there is we can find that the specific energy level, specific observation line, so that it calculated and it proposed that hydrogen has a quantum energy level. From the undergraduate course of quantum mechanics, we already studied for the hydrogen atom orbital eigenvalue and eigenfunction, and the eigenvalue can define that very well defined energy level that corresponding to the spectroscopy. But when we see in more detail the spectroscopy level, there are several degenerated states, and we can find that the additional energy level. And so, here, for example, when you see that the energy level, there is a line in the quantum level, and then when you see in more closely, and there are several more energy level like this, and the degeneracy may break down. We can see that these additional energy levels in spectroscopy can be described by the perturbations to the Gersdorf-Coulomb interaction. We call it as a hyperfine interaction. So it is hyperfine interaction. Hyperfine, here I will define what is the hyperfine interaction between electron and nucleus. Because the hydrogen compose the proton and the electron revolving around the nucleus atom, that is a proton. So, and there is an interaction between electron and nucleus. So here there is, we already know that there is a spin of the electron, and there is also magnetic moment. There is a spin here, we call it as I. Then the magnetic moment between electron and proton can interact with each other. So, and it is hyperfine interaction is the magnetic moment. Magnetic moment of the nucleus. It is originated from the magnetic moment of the nucleus, and there may have the interaction with the internal magnetic fields. There is an interaction with the internal magnetic field in the atom, caused by electrons orbital motion and by electrons spin magnetic moment. Here we already know that electron revolving around the nucleus, so it makes the magnetic field, and it generating the angular momentum and the orbital angular momentum and the spin angular momentum. So angular momentum of the orbital angular momentum and spin angular momentum can interact with the nucleus magnetic moment. So that is originated from the hyperfine interaction. So let's consider in more detail in the magnetic moment of electron spin. Magnetic moment of electron spin is written down mu e, then it is minus ge is over e over 2me and spin. Here the ge means that the gyromagnetic ratio, and in general ge is equal to 2 in the electron, and it is a gyromagnetic ratio of electron, and S means that the spin. So spin, because here here e over 2, this one can be write down as the minus ge in the mu b Bohr magneton S over h bar, because in the Bohr magneton mu b is like a e h bar over 2me. So, and this term can be corresponding to the mu b over h, mu b over h bar. So it is electronic magnetic moment by electron spin, and so there is another magnetic moment of proton. Magnetic moment of proton can be write down as a gyromagnetic ratio of proton, and the E over 2 mp, and I is that the proton spin. Here it is I is that the proton spin. In some cases, proton spin can be, we call it is isospin. So it is denoted by the I. Here proton spin water in this case also can be write down proton gyromagnetic ratio, and the mu n is a nuclear magneton, and the I of h bar. Here it is mu n, it is nuclear magneton. Mu n is that EH bar over 2 mp. It is a nuclear magneton, and also a gyromagnetic ratio of a proton is GP. It is written down 5.59, and also mass of proton is 1836 times electron mass. Then we should include the hyperfine interaction Hamiltonian. Hyperfine interaction Hamiltonian is the interaction between proton and the proton and electron. Then in the electron case, there are several interactions. The first thing is that interaction between orbital angular momentum, electron orbital angular momentum, and the spin. And the other one is that dipole-dipole interaction of the electron and nucleus. And also, so we should think that, and the magnetic dipole interaction as well as the orbital angular momentum interaction. So here let's define that the hyperfine Hamiltonian H prime means that it is a part of the Hamiltonian that is smaller than the original Hamiltonian. So this interaction between the magnetic spin and orbital angular momentum is that we can write down mu p dot mu 0 over 4 pi and also mr cube and el. Here it is orbital angular momentum and the interaction between the and the proton spin and orbital angular momentum. And second term is the dipole-dipole interaction. So you can write down mu 0 over 4 pi and 1 over r cube. And the first thing is that the electron magnetic moment interaction between the electron proton magnetic moment. And also we should exclude the self interaction, and the self interaction is that mu e dot r and the mu p dot r here like this. It is interaction between mu e and mu p at r equal to not 0. And so here then it is generally it is coming from the electromagnetics of the dipole-dipole interaction, and also should exclude dipole-dipole interaction. The dipole-dipole interaction is that the minus mu 0 over 4 pi and 8 pi over 3 and mu e dot mu p, and it is a delta function. And here it is also dipole-dipole interaction. At r equal to 0. We call it as a Fermi contact interaction. From the electromagnetics and also electromagnetics, and it can be write down like this hyperfine interaction between electron and magnetic spin. Then it can be summarized like that, and the mu 0 4 pi, it is common factor, and here GE mu b, GP mu n over h bar square, and also 2 over GE 1 over r cube, and I dot L minus 1 over r cube S dot L plus 3 over r to the 5 S dot R I dot R plus 8 pi over 3 S dot I and the delta function. Here and for the first ground state, in this term equal to 0 for the 1s ground state. So only remain for the in the case of the 1s ground state. And the hyperfine interaction is that mu 0 over 4 pi GE mu B GP mu N over H bar, and 8 pi over 3 and S dot I delta function. So we should calculate the matrix elements from the to obtain this, and we should find that matrix elements of the and here less it is the same. It is the same, and here space and delta function and space, and also spin basis S dot I and spin basis like this. So when you calculate this space bracket, and here's a space and delta function and space, it is that volume integration, and psi 1s state, and r zeta phi, and the delta function, and psi r zeta phi. It is a 1s state wave function. So because of the on-site zero, it is only survive the on-site, and so from the definition of the delta function, it is that the psi 1s state square, but r equal to 0. So this 1s ground state hyperfine interaction Hamiltonian can be write down anyway. It is anyway any kind of A is that coefficient, and S dot I here A equal to 2 pi over 3, and mu 0 and GE mu B GP mu N and psi 1s 0 square. So it means that, and when you think that here the atom the for spin case, in the spin case, and so in the antiparallel interaction, then the mu E magnetic moment, and also can interact with the isospin or the proton spin. It is the isospin and the proton magnetic moment. Then in this case that here the S and I antiparallel. S dot I is negative. It is antiparallel. So when you think that this kind of hyperfine interaction Hamiltonian, and that causes the additional energy level that coming from the so we treat this hyperfine Hamiltonian as the perturbation theory. So in the later, and we can describe what kind of hyperfine perturbation Hamiltonian can be dealt with.